Welcome everyone, and welcome to lesson 2.14 from Precalculus, which is all about logarithmic function, context, and data modeling. So we're going to take some logarithmic functions or some data that mimics that of a logarithmic function. We're going to find the equations for them and make predictions using those model equations. So let's get started. Our big idea for this lesson is that a relationship is logarithmic in nature. It has a logarithmic pattern, grows in a logarithmic way if the dependent value, the y, increases at a constant rate while the independent, the x, increases at a proportional rate, so the inverse of an exponential. So if we look here at this data, we go from 1 to 3, 3 to 9, 9 to 27, and 27 to 81. All of this is a pattern of times 3, where the dependent is going from 3 to 5, 5 to 7, 7 to 9, 9 to 11. That's addition by 2. So the independent is the one increasing proportionally, and the dependent is increasing at a constant rate. Now, the question is, what's the equation that models this? And if you can tell me what it is, I'll be super impressed. But I'm not going to tell you. I want you to try to figure it out if you want to know. So let's do some logarithmic regression, if you will. So we have some data here, and we can see that the number of students is growing proportionally. We have 2 to 4, 4 to 8, 8 to 16, so that is all being multiplied by 2. And then our temperature is decreasing. It is decreasing, well, no, our temperature is increasing. It's increasing at a constant rate. This is where my brain was wanting to go. 7 to 9, 9 to 11, 11 to 13. This is all plus 2. So what's the regression equation to model this? Well, we need to pick a logarithmic one because we're multiplying in the x's and we're adding in the y's. So if we go to our calculator here, we know that we can get started by hitting the stat button, edit, and then typing in our numbers. So we have, now we know, because the data is kind of perfect, that this is going to be a really, really nice logarithmic regression. So if I hit the stat button again, I go to calculate, I can find, well, we're going to search for a log regression, and if I scroll through, I don't see log. I see this logistic, but I don't think that's what log is. I do see a natural log, so let's pick that one. So we're going to make list 1 x, list 2 y, and we're going to store our regression equation in y1. I don't know if I've shown you this or not, but we can hit variables, go to y variables and enter, and we can store this equation for us. And we're going to hit enter and calculate, and we get an equation. Now, if you notice, it didn't give me the r and r squared statistics that we had been using previously to see how good our model was. So what I'm actually going to do is I'm going to hit mode and turn those on. Always a good idea when you're dealing with regressions to have that data just to see. So we're going to hit stat, calc 9, and we're going to do the linear regression again. Since I've already stored the equation, I didn't change the data. I'm not going to store the equation again. That's just a waste of time. Calculate, and now we get the r squared and r values, and we can see that they are 1. It's a 100% accurate model. So our regression equation is temperature is the output, so temperature per student is equal to 65 plus 2.885 s. No, log s. Mr. Whaley, you're losing your mind a little bit. It's logarithmic. Natural log of s. So that would be our regression equation. And you might be like, that's a weird decimal. Where's that weird decimal coming from? It's coming from some of our logarithms. There is a better equation to represent this, but the calculator's not going to tell us what that is. If you can figure that out, I will also be impressed. So let's use this because it is perfect, and we are storing the nice huge decimal. So let's use that for our prediction. Using the model, what temperature would there be if there was 35 students? Well, we just want the temperature at 35 then. So we can figure out that with our calculator. What I would do is I would modify our table to ask for independent values. Oh, we don't want to graph it. Oh, perfect. It doesn't show up anyway. All right, 35. And 35 gets us a temperature of 75.259 degrees Fahrenheit. Remember that you want to include your units if we're talking about like a real life phenomena that's described in units. So in this case, we're going to say 35 students is 75.259 degrees Fahrenheit. Then it's asking us to use the model to predict how many students there are when the temperature reaches 85 degrees. So what we can do is we can type 85 here, and we can graph it. Now, there's going to be a problem with using such large numbers, and that is that we have to change our window quite a bit. And that's fine, and we can do that, but you can also use some problem-solving techniques here. If this is starting at, this has been shifted up 65, and this is a horizontal line that's been shifted up 85, I can take 65 from both of those. I can get rid of this 65, and I can subtract 65 from 85, which would be 20, and see where those intersect, and they should intersect in the exact same place. So when I have to adjust my window, I don't have to go as far. So we know 85 would be, we said 20, so let's go a y max of 25. We can just make the y min 0 so we have a nicer graph to look at. I don't know if it's going to be negative or not. Let's graph and see what happens. So we got the logarithm there and the constant function there. They are not intersecting, and they're going to intersect over here on the right-hand side. So remember that logarithms grow to infinity, but very, very slowly. So let's change our window with that in mind. Let's make this 0 now, and let's make this 100 graph. I still don't think we're going to hit that yet, are we? Let's try again. Window, let's change that 100 to 1,000. There we go, we got some nice growth there. That might be enough. Maybe, it might be over here, but let's play it safe. Let's make it 1,500. And that way we want to see the physical intersection on our screen, and we see it. It's somewhere in here, but it happens definitely on the screen. So what that means now is that we can use the calculate tool and intersection to find it. So first curve, second curve, guess, and the intersection happens at the x-coordinate of 1024. So how many students would there be? Well, x is represented by s in this case, so how many students would there be? There would be 1024 students. And there we have it. So not too bad, kind of what we've been doing, just with logarithms instead of linear functions. Let's continue, shall we? So I like to drink coffee every morning, but I don't like it to burn my face when I drink it. So I need it to cool down a little bit. So here's a relationship between the temperature of the coffee and the time in minutes. So what we want is minutes as a function of the coffee's temperature. So we want temperature and then, no. We want minutes temperature. We want m of t. So the m is the output, the t is the input. So again, we're going to go to stat, and we're going to edit our table here. Remember, we're going to clear our list. We're not going to delete them. And then we're going to type in our data. So we'll start with the x's. That would be 95. Same number in both lists. That's a good sign. So off the bat, we don't necessarily know what the relationship's going to be. The outputs look to be increasing at the same amount, so maybe it's a linear function. So stat, calculate, let's try a linear regression. And linear's not bad at all, actually, considering the circumstances. Let's try a natural log regression. And that one's a little bit better. We can see that we had a 99.6 r squared, or 0.996, and now we have a 0.998. So this one is a little bit better. So we're going to use that natural log regression. And since it looks like we're making a prediction down here or using the data to do something, let's store the value because I didn't do that. So let's store this in variable y1 and have it rerun the calculation for us. So we're going to write it down just anyway so we have it. So we have m of t. It's good to use your variables for this. Is 283.47, there we go, plus, I guess it would be a minus, it's negative there, minus 62.246 natural log of t. So that's not bad. How long will it take for the coffee to be 70 degrees? We want the temperature at 70 degrees, so we can just go to our table then. So second table. We can ignore the y2. We can actually clear that out if you want to. And we want 70 degrees. We're going to type in only 70 there, and we get about 19.02 minutes. So 19.02 minutes. It looks ugly, but it works. There we go. That's not that bad. So, again, regression works the same. Not much of a difference there. What about just a regular run-of-the-mill application question? So, decibels are a measurement of loudness, and we have this function here to measure decimals by intensity of sound, and we have this nice equation here. What is the intensity of sound of a school fire alarm when it registers 100 decibels? So what we're going to do is we're going to do 100 is equal to 10, it's a regular log, the common log this time, of I over 10 to the negative 12. So first thing I would do is divide by 10. I get 10 is equal to the common log of I over 10 to the negative 12. And you have some options there. Like you could graph this, you could graph that and see what they intersect. Like that's perfectly fine. I like solving my equations as much by hand. One, I think it challenges me a little bit more. So I'm going to raise both sides to the power of 10, or 10 to the power of both sides, if you will. So I get 10 to the 10 is equal to I over 10 to the negative 12. So I'm going to multiply both sides by 10 to the negative 12. So I have 10 to the 10 times 10 to the negative 12 equals I. So 10, we have common bases. We're multiplying common bases together, which means we're going to add the exponent. So I get 10 to the negative 2 is equal to I. And 10 to the negative 2 power is reciprocal squared. So it would be I is equal to 1/100th. And that is our answer. That's not bad at all. That's actually quite nice. If we got somewhere where we weren't really able to proceed quite nicely like we did here, we could, again, use the calculator to help us in that regard. So last but not least is I want to save for a house. And my house that I want is $300,000, which I think is fairly decent for our area. If I currently have $50,000 in my bank account, I wish, and the compound interest for my account compounds continuously. Again, I wish. Banks don't work like that. If I left my money in my account for 12 years and I didn't touch it, meaning I didn't take money in and I didn't take money out, what interest rate would I need in order to achieve my goal of purchasing this house in 12 years? So I have a little cheat code for us, and it is A equals P times E to the RT power. So the amount is equal to the principal times the natural constant to the power of the rate as a number times the amount in typically years. So that is what this stands for. Many of my former students just refer to it as PERT. I won't look at you funny. I'll get the reference if you choose to name it like that. But it is the continuous compounding equation. Most bank accounts don't continuously compound. In fact, banks would lose money if they did that, so I haven't seen any that do that. They use a different formula, compound interest formula, which I would definitely recommend looking up on your own if you're interested. But for now, we're going to use this formula here. So we're going to plug in everything to where it goes. So we have the amount I want is 300,000. The amount I have is 50,000. Then we're timesing that by e to the power of whatever the interest rate is times the 12 years. And we can do a lot here. First of all, we can divide by 50,000, which there's 4, 1, 2, 3, 4, which is basically dividing 30 by 5. That's 6. So we have 6 is equal to e to the, I'm going to rewrite this as 12r. Let's write that a little bit better, 12r. I can now take the natural log of both sides, so I'd have the natural log of 6 is equal to 12r, and then I can divide by 12, so r is equal to whatever the natural log of 6 is divided by 12. So let's try to evaluate this now using our calculator. So we have the natural log of 6, close parentheses, divided by 12, and we get r is equal to 0.14931. There's a reason why I had so many decimals there, because if I write this as a percent, it would be 14.931% would be my interest rate. So again, if we're talking about a rate, you would want to write that as a percentage, so on and so forth. That is it for today's lesson. Hopefully we felt that it wasn't that bad. If you have any questions, remember to ask. Otherwise, I'll see you in the next video.